Welcome to this explainer. When most of us hear the phrase quantum physics, we immediately picture sci-fi movies or wild thought experiments. But we're going to discover how this mysterious world isn't just fiction. It's actually the invisible engine powering the device in your pocket right now, and even the literal mechanics behind evaporating black holes.
So do you already live in a quantum universe? Well, yes. You might think quantum mechanics is just an abstract playground for theoretical physicists in lab coats, but from your cell phone to the GPS navigation guiding your car, it fundamentally dictates our modern reality. It's the science of the unimaginably small, but man, it punches way above its weight.
Okay, let's take a quick look at our roadmap for today. We're going to cover 1. The quantum age, 2. The end of certainty, 3. Keeping quantum time, 4. Lasers and space-time ripples, and finally 5. The quantum computing revolution. We're transitioning from mind-bending historical theories right up to the tangible technologies shaping our future. Let's jump in.
All right, Section 1, the quantum age. Let's look at what this age actually means and why physicists consider it the absolute most successful scientific theory of the last 100 years.
At its core, quantum physics is simply the study of the unimaginably small. It was originally born in the early 20th century to solve a major headache for scientists. Does light act as a particle, or does it act as a wave? Because sometimes it acts like a wave traveling through the ocean, and other times it acts like miniature billiard balls. Ultimately, the answer was a completely new kind of physics, proving it can actually be both.
Moving right along to Section 2, the end of certainty. And oh boy, this brings us to a radical shift in human understanding, a total, complete departure from the predictable rules of the universe.
Think of classical physics, the stuff Isaac Newton taught us, as a perfectly predictable clockwork universe. You throw a ball with a specific force and angle, it follows a set deterministic path every single time. But quantum physics, it is intrinsically probabilistic. Even if we know absolutely everything about a setup, the best we can say is, well, there's a 50% chance of this outcome or a 30% chance of that one. It's not that we're missing information. Probability is just hard-baked into the fabric of reality.
Now, this shift to pure probability was so incredibly jarring that Albert Einstein famously rejected the whole idea. He declared, God does not play dice with the universe. He just couldn't accept that the deepest levels of our universe were governed by random chance. I mean, in classical physics, looking at the moon doesn't change the moon. But in the quantum realm, things are so much weirder.
This brings us to a really bizarre state called superposition. Basically, an unobserved particle is just a mathematical wave of probabilities. It exists in a combination of all possible outcomes until the exact moment we observe it. That observation literally forces the wave function to collapse, making the particle pick a single reality. And what happens to the outcomes that aren't observed? Well, that is still one of the greatest mysteries in science today.
Okay, Section 3, keeping quantum time. It turns out, we actually use these invisible, uncertain particles to keep the most precise time on Earth.
For centuries, we tracked time using the sun, swinging pendulums, or quartz crystals. But since the 1960s, we've officially defined a single second by counting over 9 billion specific energy jumps or oscillations of a single cesium-133 atom. Because the laws of quantum physics are unchanging, these atomic clocks give us a universally defined time no matter where you are on the planet.
And here's the wild part. Without those quantum ticks, the GPS in your phone wouldn't work at all. When you use GPS, your phone is checking signals from 4 or more orbiting satellites, and each of those satellites carries multiple atomic clocks on board. The signal sends a hyper-precise timestamp, letting your phone calculate exactly how long the signal took to arrive, triangulating your position down to a few yards. You literally rely on synchronized quantum timestamps from space just to drive to the grocery store.
But of course, science never stops. Today, physicists are using strontium atoms and highly tuned lasers to create quantum pendulums. These optical atomic clocks swing at a speed of nearly 1 million billion cycles per second. That makes them 100,000 times more precise than the traditional cesium clocks we just talked about.
And these optical clocks are so ridiculously sensitive, they can actually measure gravitational time dilation. Einstein predicted that gravity warps space-time, meaning time literally moves faster at higher elevations where gravity is slightly weaker. These new clocks are so precise, they can detect time running differently just by changing their elevation by the width of a human hair. No way, right?
All right, Section 4,
lasers and space-time ripples. Let's talk about a quantum marvel you've probably interacted with today, the laser.
If you want to understand why a laser is actually quantum tech, think about it like this. An ordinary light bulb is total chaos. Atoms are vibrating at different speeds, spitting out photons in random directions. It's like a chaotic mob at a rock concert singing at entirely different pitches. A laser, on the other hand, is like a perfectly tuned Juilliard choir. You've got millions of trillions of photons singing the exact same note, in the exact same phase, heading in the exact same direction. This insane purity comes from a quantum trick called stimulated emission. A photon of just the right frequency passes by an excited atom, basically tricking the electron into dropping its energy and cloning a perfectly matching photon. By trapping these atoms between mirrors, the photons bounce back and forth, stimulating even more identical photons, and boom, you get an intensely pure beam of light.
Now take those ultra-stable lasers and scale them up into massive 2.5-mile-long tunnels. That's the LIGO Observatory. In 2015, they achieved the impossible. They directly detected microscopic space-time ripples, known as gravitational waves. Einstein thought these ripples would be too tiny to ever detect. But thanks to laser interferometry, LIGO literally felt the ringing of the space-time drum caused by the violent collision of two monstrous black holes, billions of light-years away. Absolutely mind-blowing.
Finally, Section 5, the quantum computing revolution. This is the absolute bleeding edge of today's quantum applications, where scientists are leveraging the weirdest parts of physics to build the supercomputers of tomorrow.
The secret sauce here is quantum entanglement. Einstein absolutely hated this, by the way, calling it spooky action at a distance. Imagine a machine spitting out pairs of coins. You fly one to the moon and keep one on Earth. You flip the Earth coin, it's heads. Instantly, the moon coin is also heads. Flip after flip, they always match, with zero physical connection. In the quantum world, entangled particles instantly mirror each other, acting as one pure state no matter how far apart they are.
So how is a qubit actually different from a classical bit? Because to build a quantum computer and harness that spooky entanglement, engineers have had to completely rethink the fundamental building block of computing itself.
Look, every email you send, every app you use, it all boils down to classical bits, which are rigid, like a light switch, locked strictly at 0 or 1. But a quantum bit, or qubit, relies on that superposition we talked about earlier. If a classical bit is stuck at the North Pole or the South Pole, a qubit can exist anywhere on the surface of a sphere, in a superposition of both states at once. If you combine just a few hundred highly entangled qubits, you create a mathematical space so massive you'd need more classical bits than there are atoms in the visible universe just to describe it.
The physical reality of actually building these machines is just wild. Companies use microscopic loops of superconducting metal for qubits, and because even the slightest thermal noise destroys the delicate quantum state, they use these massive, beautiful dilution refrigerators to keep the chips at 0.015 degrees above absolute zero. Then they hit them with carefully timed microwave pulses. Now, to be clear, you aren't going to be playing video games on a qubit anytime soon. They're designed as accelerators to solve impossibly complex chemical simulations and material science puzzles that classical computers just literally cannot handle.
We've gone from fierce theoretical debates in the 1920s to atomic clocks running our daily GPS, lasers mapping colliding black holes, and qubits chilling near absolute zero. It leaves us with one really thrilling question. If we're already using the weirdest, most non-intuitive mechanics of the universe to power our present day, what completely unimaginable realities will quantum technology unlock in the next 50 years? Thank you so much for joining me on this explainer. Keep wondering and keep looking closer at the universe around you.